Hi everyone, so for my attack reproduction, I choose to reproduce Dan Kaminsky DNS cache poisoning attack. And here are the outlines. So first, we're gonna introduce some DNS background, including terminologies, how DNS query process look like, and what a DNS packet looks like. And then we're gonna go over DNS cache poisoning attack. We're gonna talk about how it was discovered and why it is not as powerful as the later one. And then we're gonna overview the Kaminsky attack. We're gonna analyze why it has been way more powerful than the previous ones, and we're gonna reproduce this in our lab. And then we're gonna analyze what problems I ran into during the experiment process. And the last part will be the mitigation. We're gonna go through DNS 0x20 bit encoding mechanism and analyze how effective it is against the Kaminsky attack. And to start with, DNS stands for domain name server, and its job is to translate domain names into IP address. Domain name are the more human readable, and IP address are the sequence of numerical values. For example, google.com will be the domain name, and if you pin it, it will return this IP address. .100 is the IP address. DNS hierarchy is introduced because domain namespace is organized as a hierarchical tree-like structure. So the top level, we have the root, which is denoted as a dot, and then below that we have top level domain, which is what follows the domain name in URL, and there are several categories by their purposes. For example, .com for commercial, .edu for educational institute. And below that, we have the second level domain, which is the website name. Then we have the subdomain, which can be the subset of a specific website, like different sections. And host can be the allocation resources to run or to host this whole server. And there are more terminologies. First, we have zone. So DNS is organized according to the zones, and the zone groups can teach us domains and subdomains on the domain tree and assign management authority to an entity. And we have authoritative name server. Each DNS zone has at least one authority NS that publishes the information about the zone. And it has two categories. One is master, which stores the original copies of all zone records, and also has slave, which is just doing the replicate of the master records. And we also have a root name server. So across the globe, we have 13 DNS root servers. They are the starting point of DNS queries and provide the name server about all top-level domains. And we also have recursive resolver. So it recursively trying to find the result for the zones that is not authoritative for. It's the main purpose of that is act as a service to the client. So it will talk to the client. And here is the how the DNS query process will look like. To start with, the client will initiate a request to load a domain. So the client reach out to the DNS resolver, which typically hosts in the user internet service provider. It will first check the resolver cache for a short circuit the current lookup process to resolve the domain name to an IP address. And here we assume there is a cache miss for both the browser and the operating system. So the DNS resolver will going to make a request to one of the root name server, and the root name server will respond with an IP address to a top-level domain name server. And then the DNS resolver will propagate the request query to the top-level name server. The top-level name server will respond with an authoritative name server. The DNS will then forward the query to the authority name server, and the name server will scan the zone files and try to find the mapping between the domain name and the IP address, and it will return the mapping back to the DNS resolver. So at this point, the DNS fulfilled the client's request with the IP address, which the browser will later use to communicate to the request domain. The DNS resolver caches this domain IP mapping with the time to leave timestamp for future usage. The client will then send the request to the IPA with the query, and the server will respond to fulfill the client's request. And here are the different information stored in the packets. And what we will pay attention here is the source IP address, destination IP address, source port, destination port, and the query ID. So, a little overview of how the DNS cache poisoning attack look like. The attack is trying to inject malicious IP address into the recursive resolver's cache. History of this attack. So the transaction ID was introduced as the UTP could easily spoof the responses from the authoritative DNS server and thereby poison the cache of the server. But in mid-2007, Microsoft Bind 8 and 9, they were exploited due to the extremely predictable DNS transaction ID for their outgoing queries. Still, the previous attacks has the downside of to remote attack, the attackers needs to guess the source port number and the transaction ID, which are both 16 bits integers, which is used by the query packet. And if one attempt fails, the attackers needs to wait for the valid response to be timed out before the next attempt. And here we come to the Kaminsky attack. So the main idea is trying to ask a different question every time. So caching the answer doesn't matter, and the local DNS server will send out a new query each time. And it provides the forced answer in the authority section. And why it has become so powerful and destructive? First is the specific resolver could be enforced to sending queries to an authoritative server on hijacked intention. The attackers can brute force transaction IDs and send as many fraud responses while occupying large network bandwidth. And also, insert the malicious payload of the fake response. And we're gonna move over to do a demo of the experiment. For this experiment, I am gonna run inside a Linux virtual machine, and for different servers, we are gonna use Docker containers to mimic it. Let's first check our setup. If we do doc ps, we see we currently have these many containers running. For the Wireshark and Portainer, these are for monitoring our network, incoming and outgoing. And then for the DNS server, we have DNS server, we have attacker name server, and we have the machine for the attackers and the user. And now let's go to the DNS server. What we want to do is, inside the DNS server, we want to save the attacker's zone. So if anyone wants to query the attacker domain, it will be forwarded to the attacker's namespace. And to verify that, we can go to name.conf, and we see that the attacker 33 is being saved as a zone. And now we go to user machine, and we want to double check the DNS server is configured correctly. So to do that, we can go to resolve and config, and we see that the name server is being set up as a DNS, and it also has its own name server. Okay, and then now we come to the name server of the attackers. So inside the name server of the attackers, we want to save, or we want to host two zone files. The first one is the attacker33.com zone file, and also the example.com zone file. So to do that, we can go to and we see that we have two zones, attackers and examples. And we can go inside one of the zone file to see what's inside, how it's being saved. So inside the attacker 33 zone file, we see that the domain, the name server are being listed as are being mapped to the IP addresses. So we save this forward zone entry, so whenever user calls attacker name server, it will be returned the name server IP address. To verify, we can first call the legit example.com, and before that, let me refresh the Wireshark. So now, right now, if we try to dig www.example.com, from the query here, or from the record here, we see that it calls the local DNS, and the DNS forward with the legit example.com, and it will return the legit example.com response to the user. And to experiment one thing, if we send the query directly to the attacker's namespace by doing DNS.attacker33.com attacker33.com and do this. So this will ask attacker's namespace for the IP address of example.com. So now we see that the local server forwarded to the name server of the attackers and then return the response. Okay. So the purpose of this experiment, or to verify it's being attacked successfully using DNS cache pointing, is to get the fake result from the attackers by just running the dig www.example.com. Our code structure looks like this. So we need to generate the spoofing DNS request and also the spoofing DNS responses. So to generate the DNS request, we use Grepy to implement both. We first set the destination IP as the local DNS IP address, and for the domain name, we are faking the target domain name. So we use 5 characters. We append 5 characters as a prefix each time when we send out a request packet, and this is how we construct the query packet. And now we come to see how we generate the responses. So for the IP, we are using the legit example.com IP address, and the destination is the local DNS server. Another thing to note is that inside the authority section, we set the name as example.com, but for the data, we are inserting the namespace of the attackers 33.com. And we also do the same thing to construct the reply packet. And inside the attack file, what we mainly trying to do is trying to send out the spoof request and spoof response. If we come here, we see that we have all the 26 characters, and each time we are trying to generate a random name with a length of 5. We send out the request with the spoofing name. And then to get the spoof response, we pair the name with the transaction ID. And the transaction ID increment by 1 each time, and just hope that it will match the name. And that's how we set up the attack. So now let's start the attack by running the script and see what's going on inside the Wireshark. Okay, so you see that it has been sending out the spoofing response and request constantly. Start from here. Attackers first query from the DNS for a non-existing subdomain of the example.com. And since it's the mapping between the domain name and the IP address is a miss, the DNS will query to the name server of example.com. And while the DNS is waiting for the response, the attackers will constantly trying to brute force the transaction ID to the local DNS server. So we see here the transaction ID is actually incrementing. The attackers will also provide the attacker33.com as authoritative name server. And if the spoof response beats the actual response and the transaction ID matched, the local DNS will accept and store the poisoned records in the DNS cache. And if they simply fail, it will then constantly sending out different queries and repeat the process. So the attack purpose is that inside the local DNS cache, the mapping between the example.com and its IP address will actually be replaced to the attacker's namespace. To prove that this attack works, we are gonna go to user machine and we're gonna ding the example.com. And to make it work, we are gonna go to the local DNS server and verify the cache. So we first dump out the cache and we're trying to see this cache. And now we see that this example.com is actually returning the namespace of attackers. So that means this attack is working. Thanks. Here are the challenges I met during the reproduction. So I set up the Docker containers to mimic different servers. How to monitor the Docker container incoming and outgoing network took me a little bit while to figure out. And since I'm using Linux virtual machine, I have a limit on the computational resource, which makes while it doing the attack, it has latency in response. And also, this attack is not 100% effective. So that means like there are twice or three times that the attack doesn't work. So now we come to the mitigation of this DNS poisoning cache attack. So in this paper, it proposed a DNS 020-bit encoding mechanism. So how it works is after domain name input arrives, either it comes from a server or a query from a resolver. The query fields will be transformed into either all lowercases, and then the query will encrypt it using maybe AES, and the key will be shared by all queries on this recursively resolver. And since the redout cipher block is no longer than the original query in terms of bytes, bits are read in sequential fashion from the cipher block, and the query field is read 1 byte at a time. This produces a 0x20 encoded domain name and will send to an authoritative server. And here are the complexity analyzed. So in the left graph, it shows how the search space of a attacker grows while using the encoding mechanism. So this is a simple encoding for IBM.com. The x-axis is the total number of bits available to encode the transaction identities, and the y-axis indicates the number of possible combinations. And the line A represents when DNS initiator merely just use the ID field and also a single source port. And B and C line are when using the port randomization. And the E and D are using the encoding mechanism. And inside for the red plot, it shows the redoubting probability improvement for the DNS server using only the randomized ID field and the single port. The y-axis represents the average number of 0x20 characters handled by the server. And here is the summary of this mechanism. So the strength of this mechanism is first, it makes no radical changes to the existing DNS infrastructure and no major change to the existing protocols, and it is backward incapable. However, the weakness becomes that it does not provide strong guarantees for the transaction integrity, and on average, DNS message can have an additional 12 bits of state. That's all. Thank you.